And hello everybody, here is a concept map for Calculus AB, free response year 2008. This is question number 3, and this is going to be a combination of a related rates problem, a in and out type problem, and a first derivative test. So let's just go ahead and look at the problem. So number 3, it says oil is leaking from a pipeline on the surface of a lake and forms an oil slick whose volume increases at a constant rate of 2,000 cubic centimeters. So they're giving us the change in volume. They're giving us a rate function, change in volume with respect to time is 2,000. So it is a rate function. It's telling you how much something is changing by, but it's changing by a constant rate. So the rate of flow of the oil coming in is a constant flow of 2,000. And that's going to be 2,000 cubic centimeters per every minute that goes by. So there's your rate function. It's 2,000 per minute. And that's going to be how much is coming in. So eventually this is going to turn into a in-out type problem. So that's how much is flowing in. So there's your in. The oil slick takes the form of a right cylinder with both a radius and height changing at the same time. So as the cylinder is growing, the radius is getting bigger and the height is getting bigger, so you have some sort of cylinder. So your volume is coming in, change in volume with respect to time is flowing in at that constant rate of 2,000. As it is coming in, your cylinder is getting both wider, so the radius is changing and the height is changing, so your cylinder is growing. So both your radius has some sort of change to it, change in the radius with respect to time, and your height has some sort of change to it, change in the height with respect to time. And this would be your radius at any point in time, and this would be your height at any point in time. So those two parts of the figure are changing. And they go ahead and give you the formula to find the volume. So the volume is basically base area times height. So your base area is the circle, pi r squared, multiplied by the height, how tall the cylinder gets. So that represents the volume for your cylinder. And that's all the given information. And let's go ahead and look at part A. So part A, at the instant when the radius of the oil slick is 100 centimeters. So they're telling you that R is going to be 100. So that's your instant in time. So R is going to be 100, and the height is going to be 0.5. So at the instant in time, your H will be 0.5. The radius is increasing at a rate of 2.5 centimeters per minute. So they're giving you the dRdt. They're telling you that the dRdt is going to be 2.5. At this instant, what is the rate of change of the height? So that's what they're asking for. So the change in height with respect to time is what we're going to be seeking, or what we're going to be looking for. So they're giving you all the given information, and then you're going to plug in and solve for dH/dt. So if we go look at this volume formula, and let's take that to another page. So if we have our original volume formula was pi r squared. So the area of a circle times the height. They're telling you what R is. They told you that R was going to be 100. They told you that H was going to be 0.5. they told you the change in R with respect to time was going to be 2.5, and what you're seeking is the change in height with respect to time. So if you take your volume formula that relates all these variables and you take the derivative with respect to time, this is going to produce your dv dt. And we know what dv dt was. They also gave us that information at the beginning of the problem. So dv dt, they said, was going to be 2,000. So there's your dv dt. You're going to need to take the derivative of this. Just be careful because you do have a product here. So you're going to have to do the product rule when you take the derivative. You're also going to have to do implicit differentiation since your variables would disagree, since you're deriving with respect to time. So when you take the derivative using your product rule and implicit differentiation, you're going to produce your dr dt, you're going to produce your dh dt statement, you produced your dv dt statement. You can, after you're done, you can plug in all the given information, and then you can solve for what you're missing. So you want to basically derive that and then solve for dh dt. And let's look at part B. In part B it says a recovery device arrives on the scene and begins removing the oil. So here's where the out part is. So I said it was going to be an in-out function. So this was the in. This is how much was coming in. And then now they're saying that we're going to be removing oil. So we had this amount coming in and making that cylinder grow, but then we have a recovery device coming onto the scene, and they're going to start pumping oil out. So that's going to be your out, and then this was your 2,000 was your in. So you have a in-out type situation. It says the rate, so it's going to be a rate function. So if it's a rate function, we know the area under the curve, if we integrate that, is going to be the total volume that was removed. So it says the rate at which the oil is removed is represented by this rate function in cubic centimeters per minute, where t is the time in minutes since the device began working. Oil continues to leak at that same constant rate in, so there's your in of the 2,000. Find the time t when the oil slick reaches a maximum volume. So the kind of the key here that I'm picking up on is they want a max on the volume, and we know maxes occur where the first derivative is 0 or undefined. So if we can create a function that represents the volume and then look to see where its first derivative is 0 or undefined and do a first derivative test on that, that's going to tell us whether we have a min or a max. So how could we represent the volume, the total volume? So the volume, if we wanted to take a look at that, the volume is going to basically be made up out of the total amount that came in minus the total amount that went out. And how would you find the total amount coming in? That is going to be the area under the curve from time A to time B of the 2,000, the rate of 2,000. So if we find the area under that rate function of 2,000, that's the amount coming in, minus what is the rate going out. That's going to be your rate function, which they said was the 400 square root of t. And that's going to be your total accumulated volume. So accumulated volume in minus the accumulated volume out would be your total volume. And we know mins and maxes occur where v prime is going to be 0 or undefined, or at the endpoints in some case. So we want to take the derivative of this, and that's going to produce your v prime or your dv dt. So there's your first derivative. And then if you take the derivative of an antiderivative, those are going to cancel, and you're going to be left with the 2,000 minus 400 square root of t. So if you take a derivative of an antiderivative, those cancel, and you're left with this. And where the mins and maxes occur, where the first derivative is 0. So we'll set that equal to 0. And solve for t. So you want to find that time value. And then you would want to double check it in a first derivative test and make sure that you have a sign change. So whatever critical numbers you get, if you have a v prime and a volume, in order for it to be a max, something's going to need to be going up. So the volume would have to be going up, increasing, and then would have to be going down, decreasing, and then that's going to make this a max. So you'd want to justify where you have mins and maxes by using a first derivative test. And that should get you set up for part B. And if we go ahead and look at part C. Part C, let's see if we can clean this up a little bit. So for part C, it says by the time the recovery device begins removing oil, there was already 6,000 cubic centimeters of oil that had leaked. Write but do not evaluate an expression involving an integral that gives the volume of the oil at the time found in part B. So when it reaches the maximum volume at that time, how much oil is there? So we know we're going to start with the 6,000. So we had 6,000, or is it 60? 60,000, excuse me. So 60,000 is what we started with, plus how much accumulated oil, so how much accumulated volume do we have? So remember, the accumulation function is going to be the area under the curve of both the amount coming in minus the amount going out from some time 0 to whatever time value you found in part B. So this is going to be the time that you found in part B. And how do we represent what's coming in? So what was the rate coming in? The rate coming in was the 2,000 from the beginning, minus, and what was going out, that was the r of t function that they gave you, which was the 400 square root of t. So this model here will tell you how much volume was accumulated as far as the amount going in and the amount going out, how much total volume accumulated from 0 to whatever time you found in part B, plus the original 60,000 that you started with. So that should get you set up on that one. You're just going to need to find that t value from part B. And that should be a quick walkthrough of number 3 without doing everything completely out and giving you all the answers. Remember, those are not final answers. That's just kind of the big idea and how to get started on those problems. You'd have to go through and finish and find all those particular answers for those different parts.